Today we talk about pointers. And largely speaking, there are two kinds of pointers in C++, the smart pointers and the raw pointers. And the difference between those is in ownership. And while we will talk about ownership more in the future, for now it's enough to remember this. If you own something, you clean it up. Today we talk about the raw pointers. And we've seen something very similar to them before. We've seen the references. And raw pointers can do everything that the references can, and then some more. For example, have you ever tried to put references in a vector? You can do that with pointers, but you do pay a price. There is a little bit of a syntax overhead and the infamous segfault problem. Let's dig into the details. First of all, whenever we talk about pointers, we're actually talking about variables of certain special type. And this type is the pointer type. And we can form a pointer type from a normal type by appending a star to the right of it. So just as int is an integer type and int star is an integer pointer type, or a pointer to integer type. Of course, it doesn't have to be integer. You can do that with any type. So for example, if you have a cat type, you can create a pointer to cat type by appending the star to the right of cat. Anyway, as I said before, pointers are just variables of these pointer types. So what do these variables actually hold? They hold nothing else than an address in memory of another variable. Intuitively, we can think about this address as if it were simply a large integer number, usually represented in hexadecimal system. However, C++ pointers are much better than just a number that represents an address in memory. For every pointer, the compiler basically knows two things: where the variable starts in memory and what type this variable is, and this is a crucial difference. This allows the compiler to check that we point to the correct type, making our lives easier. Which brings us to how such pointers can be created and initialized in the code. If we have some variable var, which is an integer, we can have a pointer to this variable created in one of these two ways. They're basically the same. The use of the ampersand symbol might be a bit confusing, as we've used it before in the references. But when we used it in references, we used it as part of the type, so an int ampersand represented a reference to int. While here, we use it as an operator, so we use it to get the address of a certain variable. And that's why it's called the address operator. Once we're at it, let's quickly illustrate my point from before that compiler is our friend. If we try to create a pointer to a variable of a wrong type, we get an error. Being able to create pointers is all great, but we also want to get the data out of our pointers. And for that we use the star operator. And just like with the ampersand operator, we use the star both for declaring a pointer type and then as an operator, which might be a bit confusing. But it's called a dereferencing operator, and it allows us to get the underlying data from a pointer. The compiler then is able to look at where the pointer points to in memory, and knowing the size of the underlying type, interpret the appropriate number of bytes as the underlying type, giving us direct access to the underlying variable. And just to see it in the code, if we have a certain variable var and we have a pointer var pointer that points to this variable, if we set the value to var to 42, they both should be the same, and we can show this by printing them out. And if we change the values through the pointer, it should also update the actual value, which we again can check by printing these values out. Oh, and one more thing, if we point to types which are more complex, something like std_string or something, the ones that have methods, and if we want to call those methods, we technically have to do two things. First, we dereference the pointer, we get the underlying object, and then we call the method on that object, which ends up looking something like this. So if we have a string blah that spells out blah, and we have a string pointer that points to this variable, we can get its size, for example, with this construction. So we have to dereference the pointer in the brackets, and then we can call a method on the resulting object. It doesn't look very nice, does it? So to make it look nicer, we can use the arrow operator, which basically combines the two in one operation. We're able to get rid of all the parentheses and the dereferencing and just use the arrow operator to get the size directly. Much neater, right? Okay, now it's time we talk about the main difference between the pointers and the references. And the difference is this: the pointers are reassignable, while a reference is initialized as referring to a certain variable, and you can't change that afterwards. For example, if we have two variables, var1 and var2, and we have a pointer to var1, if we now set var pointer to point to var2, we've just changed the pointer, but we didn't really change any values. But if we do the same with the references, we actually change the underlying value. We're not able to reassign the reference to anything else. This is a feature that allows us to put pointers into containers. And just to illustrate this, if we have two integers foo and bar, we can put their pointers into a vector and that all compiles. But this flexibility basically means that we can have a pointer which is not initialized to anything or explicitly initialized to point to nothing, also known as a null pointer. So for example, if we try to create a reference which we don't assign to anything, it won't compile. But we can do this with the pointers, even though we shouldn't. What we should do instead is we should either value initialize a pointer like this, or explicitly provide a null pointer inside of the brackets. The last two are basically the same. The null pointer is this special value that we set to a pointer to indicate that it points to nothing. Oh, and by the way, want to see something cool? Because the pointers get implicitly converted to bool, we can plug them into an if statement. So for example, we can write if sum pointer and only enter that if statement if the sum pointer is not a null pointer. And if we only want to do something if something is null pointer, then we just plug the negation before that. So if not empty pointer will only enter this if statement if the empty pointer is actually a null pointer. Very neat, right? And trying to dereference such a null pointer will lead to the segmentation fault, or seg fault for short. It's unpleasant, yes, but it's not the worst that can happen. Dereferencing a null pointer will always lead to a segmentation fault, so if you see a segmentation fault, it's kind of a matter of time when you find which pointer you're trying to dereference, then you fix it and everything is fine again. But if you don't initialize your pointer at all, it will point to a random address, and if you dereference it, it will interpret whatever it finds under that random address as the required type. It might segfault, but might also just return some garbage data. Welcome back to the undefined behavior land. This undefined behavior, man. Switching gears. Just like with references, sometimes we want to forbid our data to be modified if we point to it with a pointer. And of course we use const for this. The problem comes in when we try to think where do we put const around our types. Because the type int star is different from const int star, which is different from int star const, and that all is different from const int star const types. So how do we read these types, and how do we even understand where to put the const here? And this topic is complicated. It has left a lot of people with a twitching eye. But there is a trick to this, and once you know this trick, it becomes much easier to read these types and to understand where to put const depending on what you want. And the trick is to read the types from right to left. So if we have a const int star blah, we start with blah, saying blah is a pointer to an integer constant. Which means we cannot change the underlying data, but we can reassign the pointer to point to other data. So if we create a const int star blah and we point it to some variable, and we try to assign blah to some other variable, that'll work. But if we try to modify the underlying data, that won't compile. This is the most common use of const with pointers, but there are other ways. Let's have a quick look. Now for int star const blah, we start with blah is a constant pointer to an integer, which means that we can change the underlying data, but we cannot reassign the pointer to point to other data. We can quickly check that too. So for int star const blah, and we point it to some variable, we can easily change the underlying data, but if we try to reassign the pointer to something else, that won't work. Finally, there is a way to forbid any changes at all. So one final time, if we have the const int star const blah, we start with blah is a constant pointer to an integer constant, which means that we cannot change the underlying data and we cannot reassign the pointer to point to something else. Honestly, at this point, just use a const reference. And to make sure that you understand how it all works, do try the same on this. What does it translate to? This is about everything that we have to know about raw pointers. They provide us some flexibility, but we pay for it with the cost of possible seg faults and maybe even some undefined behaviors, plus a little bit more complicated syntax. The rule of thumb here is to use references whenever you can and only resort to raw pointers when you cannot use a reference instead. But they serve kind of the same purpose. That being said, understanding what raw pointers are is very important, and they become even more important when we start talking about the dynamically allocated objects, the object-oriented programming as a whole, and polymorphism in that context. Until then, thanks for watching. You can subscribe to my channel over here and watch maybe another video of mine over there. Thank you, and bye.